All right, welcome back everybody to the last topic on the unit on polygons. The shape this time is a trapezoid. So the video today will show the definition of a trapezoid, and we got three theorems to prove today. And no examples, we'll get those from the assignment. So let's start out with what a definition of a trapezoid is. So a trapezoid is a quadrilateral, again, four sides, a quadrilateral with exactly one pair of parallel sides. So contrast that with the parallelogram, which had two pairs of parallel sides, the kite, which had no parallel sides. Trapezoid has one pair of parallel sides. So just looking at some of the vocabulary associated with the trapezoid. So the parallel sides of a trapezoid are called the bases. So you can see that there in the diagram. The parallel sides are called the bases. The non-parallel sides are called the legs. So you can see those on the left and right side. Also, we have what's called base angles. So angle B and angle C at the top. These are both base angles because they're angles which include the base. But you also have another pair of base angles down here at the bottom because you have another base. So angles A and D are also called base angles because they include the base. The common side for those two angles is one of the bases. Okay, we have a particular type of trapezoid called an isosceles trapezoid. So the definition of an isosceles trapezoid is a trapezoid with congruent legs. So you see the trapezoid, one pair of parallel sides. See that marked off by the arrows. And then you see the legs, which are congruent here, so marked off by the single tick marks. So that's an isosceles trapezoid. And today we have two theorems about the isosceles trapezoid. And then the last theorem is about the trapezoid mid-segment theorem. Okay, so first theorem we have today about the isosceles trapezoid, which says base angles of an isosceles trapezoid are congruent. So what I'm going to do to prove that is I'm going to draw what's called auxiliary lines. So that's these broken line right here. So I'm going to draw that altitude from point B down to the base, the other base of the trapezoid, and we're going to call that point E here. Then I'll draw one more altitude from point C down to the other base. So an altitude is perpendicular to another segment. And we'll call that point of intersection point F. So I'm trying to prove angle A and D congruent. You can see those down there. And also angles B and C congruent, because those are the two pairs of base angles in this trapezoid. All right, so to do that, I'm going to prove those two right triangles congruent that you see there. So you see that their hypotenuses are congruent. Those altitudes I just drew are also congruent, because that's how far two parallel lines are from each other. And so you can see that the two triangles are congruent by HL. HL, hypotenuse, leg, they're both right triangles. Hypotenuse is congruent and a leg is congruent out of each. So that'll tell you that angle A and angle D are congruent by corresponding parts of congruent triangles are congruent. CPCTC. Okay, so we also want to prove that, so we got this, I'll mark that off, these are congruent. So that's one pair of base angles, but the other pair of base angles are also congruent. So I'm talking about this angle right here. I'm not going to call that angle B because there's more than one angle B there. So those two angles that I marked off with the double arcs are congruent by the congruent supplements theorem. So angles that are supplements of congruent angles themselves are congruent. So angle B is a supplement of angle A because parallel lines, these are same side interior angles. Angle C is a supplement of angle D. And we already said that angles A and D were congruent. So B and C are supplements of congruent angles, so that makes them congruent. So we've proved then the theorem that says base angles of an isosceles trapezoid are congruent. Okay, so the other theorem about isosceles trapezoids that we need to prove is that the diagonals are congruent. So what we want to do to focus, so BD is obviously one of the diagonals, and AC is the other diagonal. We're going to try to prove those congruent. So to do that, we're going to pick two triangles which have those diagonals as corresponding parts, then prove the triangle's congruent, and then say that BD and AC are congruent by CPCTC. So here's the triangles that you want to prove congruent. So the yellow one and the green one. So how are those two colored triangles congruent? First of all, they got one side congruent because the trapezoid is isosceles. So BA and CD are congruent. So we already have that. It's part of the given. Notice those two colored triangles are overlapping. And if you separated them, this segment AD would be overlapping. And so that's congruent in each of the two triangles. You can mentally like slide those apart. That's where they overlap. And so that's a congruent side in each of the two triangles. Now we also know this angle right here in the yellow triangle is congruent to this angle in the green triangle because they're base angles of an isosceles trapezoid. And we just proved the base angles of an isosceles trapezoid are congruent. So you can see that the green triangle and the yellow triangle are congruent by side angle side. Side angle side. And so once those two colored triangles are congruent, then we know that this statement that we're trying to prove is true. BD, segment BD, is congruent to segment AC because those are corresponding parts of congruent triangles, so they're congruent. So we just proved the theorem that the diagonals of an isosceles trapezoid are congruent. Okay, so we have one more theorem to prove here. Before we do that, we got to introduce one more vocabulary term here. It's called mid-segment of a trapezoid. So a mid-segment of a trapezoid is simply a segment which joins the midpoints of the legs. So you can see that mid-segment there. I got pointing at that right there. You're joining the midpoints of the two legs with a segment, and you can see it is a midpoint of both sides by the markings. And so that's called a mid-segment because it joins the midpoints of the two legs of a trapezoid. So that's called a mid-segment of the trapezoid. So we're going to use that. We're going to prove a theorem about the mid-segment of a trapezoid next. So not surprisingly, our new theorem is called the trapezoid mid-segment theorem. And here's a statement of the theorem. What it says is the mid-segment of a trapezoid is parallel to each base, and its length is half the sum of the lengths of the bases. So that's a bit much there, but let me draw this into view here, and we'll restate that theorem. So what that theorem says is this mid-segment MN, I guess I should mark that off that that's a mid-segment here, joins the two midpoints. So the mid-segment MN, there's two things the theorem says about it. It's parallel to the two bases. So it's parallel to the top of the trapezoid and the bottom. And its length is half the sum of the top and the bottom bases. So it's a little bit tricky to prove. We're going to use coordinate geometry. And so bear with me on the proof here. It's going to get a little bit tricky. So we know how by now to prove two lines parallel, just show that their slopes are equal. Before we do that, though, we're going to have to find the midpoints coordinates of these 2 points, M and N. So remember the midpoint theorem is you average the x's and you average the y's. So I'm going to average the endpoints, the x's of the endpoints Q and point P. So it's 2a plus 0 is 2a and divided by 2 is a. So this is a right there for the x coordinate of the midpoint M. Let's do the same thing for the y coordinates of points Q and P. Add the y's up and divide by 2. That's the midpoint formula. So 2b plus 0 is 2b and divided by 2 is b. So that midpoint M has coordinates of a comma b. Let's do that again for point N. Okay, so this is a little bit more complicated, but again, we're going to use the midpoint formula. So let's add the midpoints, or the x coordinates of the endpoints R and S. So we're going to add C plus 2D. So little scratch work here. C plus 2D. So we added those x coordinates, and when you simplify that, you get 2C plus 2D. Then when you divide that by 2, you just have C plus D. So that's going to be our x coordinate here, C plus D. The y coordinate's a little bit easier to do, so you're just going to add 2b and 0 to get 2b, and then divide by 2, so that's going to be b. So there's the coordinates of point N, the other midpoint. Okay, so we had to get that out of the way to get all the coordinates here. Now again, we're going to prove that these three lines here have the same slope, which means that that mid-segment is parallel to the two bases of the trapezoid. So that's what I did here in blue ink. The slope of segment QR, remember it's the change in y divided by the change in x. So we're taking 2b minus 2b, that's our top of the fraction. That's on top, and then the change in, that's the change in y. The change in x is subtract those x's. So c minus 2a, that's down here in the denominator. the top of the fraction is 0, the bottom is c minus 2a, but when you have 0 on the top of a fraction, you get 0. So the slope of this top of this trapezoid is 0. Do the same thing for that mid-segment. Let's subtract the y-coordinates. So we're doing the slope of segment MN. Subtract the y-coordinates, so b minus b on top, and then subtract the x's, so c plus d minus a on bottom. And then when you go to simplify that fraction, b minus b is 0, so you get the 0 on the top, c plus d minus a on the bottom, but that resolves to 0, so that mid-segment also has a slope of 0. Now we'll do the slope of the bottom side of the trapezoid. So again, the slope formula, subtract the y, so 0 minus 0, that's the top of the fraction. Subtract the x's, c plus 2d minus 0, that's on the bottom of the fraction. That resolves to 0 over c plus 2d, which resolves to 0. So we just showed that all three parts, the two bases and the mid-segment of trapezoid, all have the same slope. So we just proved using coordinate geometry that that mid-segment is parallel to the two bases of the trapezoid. Okay, so the last thing we have to do is a little bit more complicated. We're going to prove that this mid-segment right here is half the sum, its length is half the sum of these two bases. So in other words, MN, its length is going to be 1/2 of QR plus PS added together. So I wrote that out in a statement here. Ignore that horizontal line there. We're going to show that MN is 1/2 of the length of QR plus PS. Remember, QR and PS are the two bases. All right, so to do that, I'm going to put in the expression for MN. Well, how long is MN? MN is simply found by subtracting these two x coordinates of M and N. So C plus D minus A. So C plus D minus A. That's the length of segment MN equals 1/2. Now I'm going to get the length of segment QR. Keep scrolling back here, QR. Just subtract the x's, so C minus 2A. C minus 2A, that's where that came from. And then the other base of the trapezoid is C plus 2D. Where does that come from? That's going to be PS. Okay, so that's the bottom base. So again, subtract those x's. So C plus 2D minus 0. So C plus 2D minus 0 is C plus 2D. Okay, then to get our last step, just multiply both equations by 2. So the left side is 2C plus 2D minus 2A. The right side, that 1/2 is gone because remember you're multiplying both sides by 2. I guess maybe I could show that. Multiplying both sides by 2. That gets rid of that fraction there on the right side. So then inside the parentheses, I just simply combine like terms. So 2C minus 2A plus 2D. So you notice that the left and right sides are equal, so that proves our point. And that proves the theorem that we were just talking about, that mid-segment of that trapezoid is, its length is 1/2 the sum of the two bases of the trapezoid. Okay, so to wrap this up, there's no examples again in the notes today in the video, but I just want to wrap this up. So we talked about a trapezoid being a quadrilateral with exactly one pair of parallel sides, called the bases. The other two sides, which are not parallel, are called the legs. We had a special type of trapezoid called isosceles, and that's a trapezoid where the legs are congruent. So that's an isosceles trapezoid. Then we had three theorems about trapezoids. The first theorem said that the base angles of an isosceles trapezoid are congruent. Both sets of base angles, remember, an isosceles or any trapezoid has two pairs of base angles. Each pair of base angles, again, includes that parallel side. So base angles of an isosceles trapezoid are congruent. Not any trapezoid has to be isosceles trapezoid. I think I made that mistake just now. The second theorem that we had was that the diagonals of an isosceles trapezoid are congruent. So the diagonals of an isosceles trapezoid are congruent. It has to be isosceles, otherwise the diagonals are not congruent. And finally, the one we just proved that you're looking at here on the screen, and that is that mid-segment of the trapezoid is parallel to the two bases of the trapezoid, and its length is the sum of the other two bases of the trapezoid. And that goes for any trapezoid, not just an isosceles trapezoid. Okay, so there's all you need to know for our last section on polygons, and so that's trapezoids. So let's get some practice working some problems. Okay, good luck, and let's work some problems again.